Hey everyone, thank you for coming out. This is an intro to Nervos CKB. My name is Matt. I used to work with prehistoric financial systems. Then I got really interested in Bitcoin. Started an Ethereum meetup here in San Francisco. Started a co-working space called Starfish and got really interested in Nervos over the course of the last year. So I've been doing a lot of writing, events, things like that. And from here, let's go from infinity to beyond. So CKB stands for Common Knowledge Base. What is common knowledge? Common knowledge is known by everyone or nearly everyone, usually with reference to the community in which the term is used. So a stop sign is a good example of common knowledge. When I see a stop sign, I know to stop, and everyone else knows to stop as well. So with that, society can function more efficiently. We all know everyone's going to stop, so we don't think about it, it becomes automatic. A green light is also an example of common knowledge. So with that, let's go. So common knowledge in a Bitcoin context is all of the balances and transactions, everything that's happened. Everyone in the network knows that everyone else knows that the same information. So we can all treat that as money. So Nervos CKB is a blockchain. Nervos CKB is a blockchain to store common knowledge. So this means not just money. And to explain that, we first need to look at state. So what is state? It's this data that can be acted upon on a blockchain. In Bitcoin, it's the pieces of digital gold and their owners. In Ethereum, it's the balances of the different users. It's a current snapshot of the network, so this is always changing. And it's required by the full nodes. So in Nervos CKB, this state is stored in cells, and we'll get to that later. So these cells can do anything. They can be programmed and strung together. So a big question is, why create Nervos? Why start a new public blockchain? Why go through the great expense and all the work and line up all the different relationships and pray that nothing goes wrong? And especially when we already have all of these systems that do all these magical things. We have EOS that does 3,000 transactions a second, Ripple that does 50,000 transactions a second, Tron with 2,000 transactions a second. So you would think we would all be celebrating these great technical achievements. But that's not true at all. We have all these terrible headlines that blockchains don't scale, and blockchain is crappy technology, blockchain's not good for payments. And we have to ask ourselves, why is this the case? And it's this blockchain trilemma. So this was proposed by Vitalik Buterin, the inventor of Ethereum, a few years back, and it says that we can only have 2 of 3 of these qualities in a public blockchain. So we can have scalability, we can have security, but we can't have decentralization. We can have scalability, we can have decentralization, but we're not going to have security. Or we could have security and decentralization, which the blockchains that people are most familiar with do have, but they don't have scalability. So we're talking about Bitcoin or Ethereum. So these blockchains are decentralized, they're censorship resistant, they have security through high attack costs, but unfortunately they don't scale. So we have people that have gone in the lab and very smart people that said they're going to fix this. So a lot of these systems have taken out the decentralization piece to say we'll just have security through cryptography and distributed nodes, and we'll have scalability. So we'll have lots of transactions, we'll have low fees, and does this fix things? So we can see where they're coming from. This is a graph of Bitcoin transaction fees. So you can see when blocks are not full over to the left, the cost of using the blockchain is basically 0. And as blocks get to be about 80% full, 90% full, the cost increases exponentially. So we can see how this has been done. So Bitcoin blocks are about 2 megabytes every 10 minutes, and Bitcoin SV blocks are 2 gigabytes every 10 minutes. So this is a 1,000x difference. This is a drastic change because we need to onboard a lot more people onto a blockchain. So for perspective, this would be like going from a person that owns a Tesla to a person that owns Tesla. So this is a very drastic change. And we can see that the fees have gone almost in the other direction, where Bitcoin Cash, Bitcoin SV, we're jamming through a lot more transactions, but fees are much, much lower. So the fees in 1 day of Bitcoin equal the same amount of fees that 365 days of Bitcoin Cash and Bitcoin SV. And we still have these headlines. Yeah, we still have these headlines, and we also have more headlines. So 98% of BSV transactions are used for writing weather data on the blockchain. 75% of EOS dApp transactions are made by bots. And why is this happening? It's because of the tragedy of the commons. So the tragedy of the commons is about a public resource that gets abused if you don't have an appropriate cost for using it. So like the roads, if a lot of people are driving, the roads are going to be unusable. So what can we do about this? We can take this blockchain trilemma and we can split it. We can use layers, just like this cool guy keeping warm with layers. So at the bottom layer, we can address security and decentralization. This is with the Nervos network. Layer 1 is for verification. So we're not doing actual computation on layer 1 of the blockchain. It's just for verifying computation that's happening at layer 2. So on the second layer, we can then address scalability. So that's computation. So all of the transactions that people are doing, we can get out of layer 2. And this allows us to make trade-offs. So at layer 1, we can be very secure, we can be neutral, while layer 2 addresses scalability, usability, and also regulation as well. You can have a permissionless blockchain that is not governed by certain jurisdictions, while at layer 2, you can have companies that run these systems that are subject to certain regulations in different jurisdictions. Layer 1, you have broad consensus by all nodes. It's a shared resource. You want to use that effectively or efficiently. And it's a source of trust for layer 2 protocols. So you can see layer 1 is this shared single layer, while layer 2 is separated. So all of the nodes in the network all know what's happening on layer 1, but that information is separated at layer 2. So with layer 2, you can have higher transaction capacity, faster transactions, and privacy, and that's because these transactions are just peer-to-peer between different users on the network. The layer 1 blockchain doesn't know about all the things that are happening at layer 2. So let's talk more about layer 2. With layer 2, most transactions are private, peer-to-peer, and they're not communicated to the blockchain. And there's an assumption that others in the network will be honest, and if they're not, then the users can use the blockchain to intervene. So this assumption of honesty is not about people stealing your money or anything like that. It's operational honesty and safety. And if there's ever any problems, then users always have the option to use the layer 1 blockchain to correct any problems. So how does layer 2 work? It's similar to a bar tab. So if a guy walks into a bar, ask that bar if they accept Bitcoin, they're going to say no, and then he's going to put down his credit card. And with that credit card, the bar may do a pre-authorization, a certain charge for kind of like a reasonable amount that the person would spend. And then as that person goes back to the bar, his card is not getting charged every time he goes to the bar. The bartender is keeping track of how much he's spending, and then when he's ready to leave the bar, then the bartender will charge his card. So this is similar. There's a transaction that's done on the layer 1 blockchain, and then peer-to-peer, those parties in the transaction can update what will be put on the layer 1 blockchain eventually when they're ready to close out their bill. So layer 2 solutions, these are words you may have heard before: Lightning, sidechains, Plasma, state channels. And again, we're brought to this question of why build Nervos? If we have all of these layer 2 solutions and all of these existing blockchains, why do we need to create another blockchain? So we can look at layer 2 challenges in Bitcoin. So the protocol is really designed to only move BTC. So it's limited, and there's no shortage of Bitcoin improvement proposals that have been put out there to broaden the protocol, but doing so would require updates that take years and upgrades that require unanimous agreement. So soft fork, hard fork, things like that. We also have layer 2 challenges in Ethereum. So there is some functionality in Ethereum that is hard-coded, even though the smart contracts are all general purpose. The cryptography that underlies Ethereum is for the most part hard-coded, and that has implications in supporting layer 2 protocols. So we also have acceptable costs for doing on-chain transactions in ETH 2.0. So most dApps are just fine with doing transactions on Ethereum today. There's very little push to move things to layer 2 to make more efficient use of the shared resource. And as ETH2 comes, we'll see even more throughput, which will, again, push things away from people having to make efficient use of that layer 1 chain. Ethereum is also designed for computation and not assets, so something like double spending ERC20 tokens has to be taken care of by the smart contract. It isn't fixed in the protocol that you can't double spend assets. So that's always something that needs to be taken care of as layer 2 protocols are coded. So with Nervos, we have a layer 1 built for layer 2. So the first thing is permissionless upgrades. So with Nervos CKB, hard forks are not necessary. If any of the underlying functionality needs to be upgraded, it can be done permissionlessly and in protocol by the users. There's also a low-level virtual machine that supports any kind of layer 2 functionality. And we're brought back to what is state. So Nervos stores its state in cells. So cells can contain any kind of data and can be programmed to do anything. So this is the cell model. And cells are the smallest unit of life. So cells can be strung together to do all sorts of things. And this is what the cell model looks like. So this is a transaction. So every cell, or every transaction takes in input cells and then creates output cells. So these input cells are similar to the UTXO in Bitcoin. So once cells are input to a transaction, they're marked as dead and they can't be used in another transaction. So this is similar to preventing double spending of assets. So you can see even output cells can be used as input cells to other transactions, and this is how cell transactions can be strung together. So almost all executing code is in cells, and cryptographic functionality is easy to upgrade. So this enables the users of the platform to continue to upgrade the core functionality of the protocol on Nervos CKB. You also have a certainty of transaction outcome. So when I send this transaction, I'm specifying input cells and output cells, and if the virtual machine of Nervos CKB doesn't compute those output cells for the input cells, then the transaction is going to error out. Whereas on Ethereum, if I submit a request to the world computer, that computer is just going to do whatever I asked it to do, and it will execute based on how it's been programmed. I have no sort of control over the output. Users also always own their own assets, so the cells are owned by owners similar to how users own their Bitcoin, whereas say ERC20 tokens on Ethereum are owned by the smart contract that is just programmed to allow certain users to use them. We also get parallel processing of transactions. In Ethereum, all the transactions need to be processed linearly. What happens in the first transaction of the block could affect what happens in the second. Whereas in the cell model, all those dependencies are specified explicitly. So a node can divide up processing of the transactions because it will know what transactions don't affect others. The cell model also enables light clients, and this is similar to SPV proofs in Bitcoin. Cell scripts, so every cell has two types of possible scripts. The first type is a lock script, so this is for use of a cell. This can be a simple owner, this can be a multi-sig, this can have a time lock. So this is similar to the scripting capabilities of Bitcoin, and also has a typescript, which allows for more robust functionality similar to something like Ethereum. So what does this look like? So these are tokens in a cell. The two cells at the top would be a owner cell. So Alice owns 10,000 of these test tokens, and Bob owns 40,000 of these test tokens. And then if they ever were to move these test tokens or do anything with these cells, then they have a reference to what is defined as test token. But the ownership of these cells is by these owners, by those keys. So the second requirement is user-owned state. So in Nervos CKB, the CK byte tokens allow a user to store data on chain. And this is small amounts of data, so say 100 CK bytes to store tokens. So this is different from other blockchains that I just pay transaction fees and then my data will stay on chain forever. This also provides a mechanism that users can remove their state as well. This provides a market price for state storage and also provides incentives for users to remove state. So an example of this would be if I had worthless airdrop tokens on Ethereum, I would never delete those. There's no reason to, and there's no mechanism to do that as well. Whereas on Nervos CKB, if I had worthless tokens that were worth less than the CK bytes that were being used to store them, then I could just delete those tokens and then sell the CK bytes on the open market. So you can see an incentive to remove old state that's not being used anymore. And this gets into sustainable economics. So a bounded state. Because the CK bytes are what enable users to store state on the blockchain, the issuance of the CK bytes limits how much state is stored. So this allows for the full nodes to stay small, or at least to be controlled, and this should allow for a network of decentralized low-cost full nodes. There's a base issuance that's similar to Bitcoin. You can see the issuance curve here, so this halves every 4 years. And there's also a secondary issuance. In the Ethereum community, this is referred to as state rent. So this is a cost on storing data on the blockchain. So instead of just paying once for a transaction fee and then occupying state for free forever, on Nervos, if my CK bytes are being used to store data on the blockchain, then I'm getting hit with inflation. So I am incurring a cost for using those CK bytes to store data. There's the Nervos DAO, which allows CK byte owners to lock their tokens in the DAO and to receive compensation that offsets that inflation. So with the Nervos DAO, the CKB is able to, at the same time, to impose a tax on users who are using their CK bytes to store state, and at the same time provide compensation to CK byte owners who are not. So the CK byte owners who have put their tokens into the Nervos DAO are holding tokens that are like Bitcoin. These are hard capped, and a user would always own a certain percentage of the total issuance. Number 4, a store of value. So a store of value is something that's secure, it moves rarely, and it has a limited supply. So with a store of value chain, you can see you have a very high attack cost. Now, why is the cost to attack Bitcoin $750,000 and the cost to attack Ethereum only $100,000? And part of this comes from Bitcoin's ability to capture value from the amount of value that's being stored on top of it. So we have this incentive system where demand for BTC increases the BTC price, and because the mining reward is denominated in BTC, this also increases the mining reward and then security. And with increased security, the demand for Bitcoin can increase as more value is stored on the blockchain. So is it possible to create a similar thing with smart contract platforms? So today we see this heavy asset problem where the value of assets secured, say by Ethereum, can increase significantly without the underlying currency appreciating at all. So without this means to capture value, the cost of attacking the blockchain is getting out of sync with the amount of value that's stored on top of it. So we want to see this dynamic of as more value is stored on the blockchain, the cost to attack the chain is increasing as well. So on Nervos, we have worked to replicate the same thing. So because CK bytes are required to store assets on the Nervos CKB, we can translate demand to store assets into increased CK byte demand, and in turn increase CK byte price. And because the mining rewards of Nervos CKB are denominated in CK bytes, we have an increased mining reward, increased mining security, and that should increase demand to store assets. A couple more things about CKB. Proof of work consensus with adaptive throughput. So as the network becomes more tightly connected, the proof of work algorithm can adjust to allow more data to flow through the network. And if there's too much data that's moving through the network at any time, the proof of work protocol can slow down as well. There's a low-level virtual machine, as we covered before. Any programming language can be supported. The focus is on JavaScript and C initially, and it can even run other VMs. So the Ethereum virtual machine, WebAssembly, etc. So with that, I'd like to thank everyone for coming today and open it up to questions.